Good. So I guess those who are still joining will join us on the way. And let me start to present you. Today I will focus mostly on some main projects which and research techniques which I was working with before. And next time it will be on Thursday. We will discuss more like future plans and research techniques which are planned by me to be used at Nazarbayev University, and hopefully some of you will be interested. Okay, guys, so let me try to change the screen. Okay, do you see my screen now?
Yes.
Yes.
Okay, cool. So somewhere here was this spotlight. Okay. Good. Okay, so this is a short outline of my talk today. And first I will start from a short overview of my expertise and research background. Then we will discuss in more details generation recombination processes in organic solar cells, introduce as one of the key technique in my research a bit more impedance capacitance spectroscopy, and also we'll discuss at the end near IR, near infrared photo detectors based on organic semiconductors. Also kind of important part of my previous research. So originally I'm from Ukraine. I did my undergraduate and master at Chernivtsi National University. It's in the western part of Ukraine. And then I did my PhD at National Academy of Sciences of Ukraine in field of solid state electronics. Mostly I was working at Chernivtsi National University and National Academy of Sciences of Ukraine with organic semiconductors, with inorganic semiconductors. So it was later this shift happened to organic and hybrid semiconductors. Then I spent short research stay in the framework of Green Talents program at Helmholtz-Zentrum Berlin, where I was working with graphene and some hybrid organic and inorganic heterojunctions, and came back for a short stay as assistant professor at Chernivtsi National University. Then got an offer for postdoc at University of California, Santa Barbara, in the Center for Polymers and Organic Solids, where actually I really shifted my research interest from inorganic to purely organic semiconductors. After 1 year within the framework of Alexander von Humboldt Foundation, I came back to Helmholtz-Zentrum Berlin, spent 2 years there working on perovskite hybrid organic and inorganic semiconductors and solar cells. And after these 2 years, came back to University of California, Santa Barbara. Apparently they were missing me, so they invited again for 2 years and a half. And currently I joined Department of Physics at Nazarbayev University as a faculty member, assistant professor. So just very short discussion of my main research projects on in these institutions where I was working on hybrid and organic semiconductors. In particular at Helmholtz-Zentrum Berlin, I was working on two-dimensional heterobilayers of graphene and organic semiconductors. Also on photodegradation of perovskites. So unfortunately, these hybrid perovskite materials, despite very high efficiency, possess quite low photostability, and also radiation hardness of perovskites. So from one side, they can be quite damaged by regular sunlight, and from the other side, they can withstand quite high doses of radiation, so bombardment by high energy protons, and possess way higher stability in terms of radiation damage than classical silicon photodiodes or solar cells.
Sorry, can I ask a question?
Yes, yes, sure.
So what is perovskites?
Yeah, 1 second. Yeah, I just had some pop-up window. Sure, first of all, good that you asked a question. So if you have any questions, interrupt me, please, so we discuss it in the process. It will be way more convenient, I believe. So regarding perovskites, it's a hybrid organic inorganic material. So most common is, do you see my like this mouse?
Yes.
Yes, yes.
Okay, yeah, good. Because somehow with this red dot, it didn't work properly. I had some weird windows popping up. Okay, so this is the most common hybrid perovskite, which is methylammonium lead iodide. So it consists of two, let's call in general, it consists of two frameworks of organic framework, which is methylammonium, this organic molecule, and another framework, which is inorganic, which is lead iodide. So it forms its unique crystalline structure in which lead iodine forms some frame, and these methylammonium molecules are embedded in between lead and iodine atoms. So in total, it's a direct bandgap semiconductor, which possess very promising properties for applications in photovoltaics and optoelectronics. The biggest challenge for nowadays, so quite high efficiencies were achieved on these materials, up to 23% solar cell efficient. However, the biggest challenge is to get stability, photostability of this material, because as you can see here, if you shine with UV light for quite long time, and UV light also present, not much, but also present in the sunlight, we end up from this nice polycrystalline perovskite film to just drops of lead. That is the only truly stable material. And understanding of these photo-induced instabilities is kind of a very crucial material science problem.
Okay, thank you very much.
Yeah, you're welcome. So yeah, if you have any questions, please interrupt me. And there was one project like this fine art of thermoelectricity was kind of started from doing some research for fun, but later we actually even published these results, and was quite interesting, unexpected result. So here we played with pencil drawn traces on paper and also drawn by brush. P.PSS is some organic degenerated semiconductor, very conductive, and put them together and made some thermoelectric elements. So this kind of pencil and brush drawn thermoelectric elements could generate some voltage and current at the presence of some gradient of temperature. So it was quite a nice project to work on. Yeah, so here next, this is what I have done in terms of organic semiconductors, pure in University of California, Santa Barbara. By the way, it's like really beautiful campus, just in between ocean and mountains. Yeah, very, very nice place. So one of the main projects was doping of organic semiconductors. If it's very established in inorganic semiconductors to dope them to have N or P type conductivity, and we have very good understanding of processes, how it works. However, in organic semiconductors, it's a bit more challenging, and also stability issues are present. That's why it is important to develop new techniques and investigate them, understand mechanisms of doping. Then generation recombination in organic solar cells, that's main part we are going to talk about today. Ionic organic electronic ratchets, which combine some structure of organic field effect transistors, which are modified by adding organic salts in the active layer. So we can modify work function by stressing these devices in external electric field. We can modify work functions of source and drain electrode, and that will allow us to convert some radio frequency signals or some electromagnetic noise present in environment to useful DC current. Also there are organic photodiodes, so that's another topic we will discuss in more details today. Okay, so what do you associate with word plastic? So I believe that something like packages. What ideas do you have else?
Yeah, like
Polymers,
waste.
probably.
Yeah, waste, and that kind of a problematic question nowadays. It's true. What else? Maybe electrical insulators. We know that all wires are wrapped in some plastic insulation, so they don't short circuit. And somehow conductive materials or semiconductive materials do not fit in our imagination quite well to this word. But however, starting from 70s, people discovered very interesting polymer, polyacetylene. And because of its pi-pi chemical, alternating pi-pi chemical bonds, where we have not just one covalent, but also two pi-pi connected chemical bonds between carbon, we have some delocalization of charge carriers all over this polymer. Delocalization means that charge carriers within this polymer can move. So if you apply some external electric field, we can force by this electric field, like driving force, to drift this charge carrier along the chain. And when it reaches edge of the chain, because these chains of polymers are quite long, there are many repeat units in a polymer chain. But at the edge, there is some chance for hopping, like jumping of electron or hole, like positive charge carrier from one chain to another, and then move again along this polymer chain. So this was kind of very groundbreaking research result, because for the first time, scientists could achieve electrical conductivity in plastic materials. Actually, this polymer looks like some piece of plastic. However, it has this unique chemical structure, which further was developed, and more advanced organic semiconductors were introduced. For this invention, 3 scientists got Nobel Prize in chemistry in 2000. And the first one, Alan Heger, he actually is a physicist, but got Nobel Prize in chemistry for his pioneering work in organic semiconductors. He established the Center of Polymers and Organic Solids at University of California, Santa Barbara, where I had the chance to work for several years. So this field of organic semiconductors developed quite rapidly, and nowadays we have really industrial scale application of organic light emitting diodes and organic field effect transistors. So you can go to the store and buy organic light emitting diode TV or monitors, and they possess unique features in comparison to other technologies. So in parallel, this organic photovoltaics was also actively developing, and because of additional levels of functionality, means they provide flexibility, at some point even stretchability of these organic semiconductor-based devices. It also gained some practical application over time. However, this large-scale application, industrial application of organic semiconductors is still in development, and there are still many scientific questions which should be addressed and understood in a better way. So that's why one of the active direction in research in field of organic solar cells is understanding generation recombination processes. Let us consider that solar energy is one of the alternatives to fossil fuels, and it's not only one form of renewable energy which can be utilized. However, it plays an important role in the development of renewable energy sector. And we know, well, we can roughly classify all organic solar cells in terms of materials aspect. In inorganic, like they are presented with mostly with silicon or cadmium telluride solar cells. Also with organic, purely organic plastic materials, and hybrid. So we mentioned about these perovskites. Nowadays, it's very actively developing direction of photovoltaics. So all of these types of solar cells, they possess some advantages and disadvantages. So there is no ideal combination of properties, of features of these materials. So for instance, inorganic, they have high performance, high stability. However, they cannot be flexible and cost quite a lot. This like material, you need to purify to high extent, get single crystal or high quality polycrystalline material, use quite high temperatures in processing these materials in order to make solar cells. So organic solar cells, they are of low cost. You can spin coat this solution process, either spin coat or print these solar cells from solutions in different solvents, which doesn't require high temperatures. That is a big advantage. They can be flexible. However, still like moderate performance is constantly increasing and quite rapidly recently. However, still lacking behind the best examples of inorganic solar cells, and also moderate stability. So that's another topic of research, stability of organic solar cells. So in terms of perovskite hybrid, we have low cost. They are also solution process. High performance, they are comparable to inorganic semiconductors. However, they are not so flexible. They have crystalline structure, so you need to make very thin layers in order to achieve some flexibility. So it's intrinsic feature of plastic organic semiconductors to be flexible, and a very low stability. That is the biggest issue for real application. So let us consider main characteristics and working principles of organic solar cells. So here you see a device structure, very common device structure, where we have some electron collecting and hole collecting electrodes on some glass substrate, or it can be some plastic flexible substrate, and active layer in between these two electrodes, which are anode and cathode. So here you have an energy diagram of this device, and the interesting feature of organic and perovskite solar cells that the material of the active layer is an intrinsic semiconductor. So usually, so that's what we want to have. Sometimes there happens some unintentional doping because of some impurities yeah, so we don't control this adding of some impurity atoms. They can cause a certain level of unintentional doping. But ideally, it should be intrinsic semiconductor. That's why we have uniform electric field between anode and cathode, which is formed because of different work functions of cathode and anode. So initially they possess different work functions, and then when we put everything in contact, we get Fermi level equal for all cathode, active layer, and anode, and that causes band bending in the active layer, and it is intrinsic, it is internal uniform electric field. Since we have this internal electric field, if we generate a charge carrier by absorbing light, this internal electric field will split these electron hole charge carriers in different directions. So electrons will be collected by cathode and holes will be collected by anode. So once it happens, they can go to external electrical circuit and produce some current. So here we have a JV curve characteristic of this solar cell. It's very general JV characteristic, which is true for all types of solar cells. And there are key characteristics which should be taken into account. First of all, it's open circuit voltage. It's voltage when we get zero current flowing through the solar cell. So it's one characteristic. Then there is short circuit current. It's when we have zero voltage drop over solar cell, so it's short-circuited. It's maximum current which can be generated by solar cell under short circuit condition. And there is also this maximum power point. So this is some maximum power which can be extracted, electrical power which can be extracted from solar cell under given illumination conditions. So obviously that at short circuit current, at short circuit condition and at open circuit condition, we don't extract any electrical power because here, oops, sorry, let's come back. Because here we have zero voltage, some current, but zero voltage. So the product of current and voltage is zero. And the same here, some voltage, but zero current. So that's why we need to be at some position where we can extract maximum power. And this maximum power is defined by the fill factor coefficient. Fill factor coefficient is a ratio of maximum power, which is product of maximum current and maximum voltage. This is maximum current and maximum voltage here, to the product of short circuit current and open circuit voltage. So the performance of solar cells, which is photo conversion efficiency called, and considered to be the most practical and important parameter of solar cells, is the ratio of maximum output power to the input power, which we, this is like power of sunlight per square meter, which we, or like per active area of the solar cell, because it can be different area. So which we apply to the solar cell. And that's why it's product of short circuit current, open circuit voltage, fill factor, and divided by this input optical power, which we shine on the solar cell. We see that all these three most important photoelectric parameters are in nominator, and that's why idea is to increase as much as possible all of them in order to get higher performance. This is general equivalent circuit of a solar cell, which represents photo current generator, diode, because of this non-uniform electric field it possesses some rectification features. So you can see this dark line, this dark JV curve. At reverse bias, current is very small, but at forward bias, it rapidly exponentially increases. Also, there is some shunt and series resistance. Obviously, for increasing performance, we want to make this shunt resistance as big as possible and series resistance as small as possible. So we have a minimum voltage drop over this series resistance, and that will allow us to extract more current from the device. Okay, so do you have any questions on the working principle of solar cells?
Sorry, can you tell again what is PCE? I mean, how is it?
PCE is photo conversion efficiency.
Okay.
Yeah, so it tells us in percent, I mean, in fraction of unity, how efficient is our solar cells in terms of converting photo energy in electrical energy. Okay, so let's go further. So here is some PCE, like photo conversion efficiency, as a function of time for organic solar cells. We see like from early 2000s started this work, and it was constantly increasing. And until 2016, something like that, most of solar cells, organic solar cells, they were using Fullerene-based acceptor material. I will explain you what it means a bit later when we have discussion of generation recombination processes in organic solar cells. But most of these devices were using non-Fullerene materials as one of the component of organic solar cells. However, recently, organic chemists synthesized new types of so-called non-Fullerene acceptor materials, and it's like some general structure of this type of molecules. And we see quite rapid increase in performance of single junction and multi-junction organic solar cells. Actually, it's a bit out of date information because it's changing quite fast. In this year, maybe early this year, was a report on 18% efficient single junction organic solar cell. So that is really increasing and coming closer and closer to this level of top performances of inorganic and perovskite solar cell. So the big material science aspect is to shift our research from the Fullerene-based acceptors to non-Fullerene-based acceptors. And there is not only one benefit in terms of increasing performance, but designing this type of molecules, design approach is very flexible. You can make very different types of molecules like this. However, with Fullerene, when we have this ball, like carbon molecule, carbon atoms ball, design flexibility is very limited. So you have this ball and you can attach something to it. However, you cannot design the core of the molecule. It's already defined by this Fullerene structure. Here, you can be very flexible. So let us consider main photoelectric processes in organic solar cells. They are different from inorganic, and that's why we should really focus our attention here. So because of low dielectric constant of organic semiconductors, it's about 3. It's how much this material reduces external electric field inside the material, in how many times. So the interaction between photo-generated electron, negatively charged electron, and hole is quite strong. That's why we form, instead of free charge carriers, which are formed in inorganic semiconductors, we form some so-called excitons, like electrostatically bound electron and hole pairs. So since they are bounded within this electrostatic interaction, we cannot split them with internal electric field and make them contribute to to external current in the external circuit. That's why what was proposed to use a mixture, so-called self-organized nanocomposite structure of donor and acceptor materials. So we dilute 50% of donor and acceptor material, and then just spin coat it. By interaction between these two materials within self-organization, you don't design the morphology of this blend. It forms a nano-composite mixture of donor and acceptor, two different organic semiconductors with different HOMO and LUMO levels. So HOMO and LUMO levels, in analogy to inorganic semiconductors, it's top of conduction band, HOMO level, and LUMO, which is lowest unoccupied molecule orbitals. It's the bottom of the, LUMO is the bottom of the conduction band, and HOMO, highest occupied molecule orbitals, is the top of valence band in traditional inorganic semiconductors. So by adjusting appropriate energy alignment between donor and acceptor material and having appropriate nanocomposite structure, this photogenerated exciton can diffuse for a very short distance before they annihilate, recombine. It's about 10-20 nanometers. So that's why morphology of this nanocomposite mixture of donor and acceptor materials in the active layer of organic semiconductors is a very critical parameter. If we have two big domains of donor and acceptor material, it will cause a problem, because our photo-excited electron hole pairs will not diffuse until the interface and recombine before. If we have two small domains, so this mixture happen that our domains are too small, then it will be very difficult to extract these charge carriers from the active layer. So there should be a balance between size of the domains of donor and acceptor. So once this exciton reaches interface, because of energy difference of LUMO of donor and LUMO of acceptor, and the same for HOMO, this energy difference can be used to split the exciton and create free charge carriers. It's so-called hole positively charged in the donor material and negatively charged electron in acceptor material. So then in ideal world, they would be just transported through these networks of donor and acceptor material and collected by anode and cathode. However, in real life, there are problems. First problem, called Geminate recombination, is recombination of charge carriers from the same exciton. So instead of being separated completely, they can come back and recombine at interface. So it means that we lose this exciton, photogenerated exciton, and we don't want to do this because this causes loss of our photocurrent. So this is one mechanism of recombination. There is another. Even if they are splitted and already move towards electrode, they can recombine on their way. And it's called non-geminate recombination, when electrons and holes from different excitons, or when after the separation at the interface, they can still meet each other and recombine in this active layer. So we get different types of non-geminate recombination. It can be bimolecular, when we have direct contact of electron and hole in the active layer. They meet each other within some cross-section area and recombine. It's also can be called band-to-band recombination, recombination of electron from the conduction band and hole from the valence band. and also trap-assisted recombination. So if we don't have just ideally pure semiconductor, there could be some traps, some impurities which create energy levels within the band gap, forbidden gap between conduction and valence bands, and they facilitate recombination processes via these traps. So obviously, it is necessary to, in order to understand how and quantify all these processes, photoelectronic processes in organic solar cells, we definitely need to investigate in details generation and recombination processes. So here is an example of ideal, this black line. We can call it kind of ideal current voltage characteristic of a solar cell. So if we add, so we don't have any geminate and Shockley Reed Hall or trap-assisted recombination. So trap-assisted recombination, also called Shockley Reed Hall recombination, because of statistics which describes trap-assisted recombination, was this equation was derived by Shockley, Reed, and Hall, three scientists, and they got this this type of recombination also can be called as Shockley Reed Hall recombination. So if we have no geminate recombination and trap-assisted recombination, we have very close to ideal solar cell. We have high VOC, open circuit voltage, high short circuit current, a high fill factor. You see that here is maximum. We don't lose much because our maximum current and voltage will be very close to short circuit current and VOC. And PCE, photo conversion efficiency, is determined by the product of these three parameters. So all of them are large and performance is high. However, if we add this geminate recombination, it means that we don't generate charge carriers, free charge carriers. And only concentration of photo-generated free charge carriers defines how much quasi-Fermi levels, which describe their concentration, are splitted in the semiconductor in the material of the active layer. That's why we lose VOC, because we have less free charge carriers, we have less splitting of quasi-Fermi levels, and we lose in short circuit current, because if we have less free charge carriers, there is less to be collected with electrodes and contribute to the short circuit current. Then if we add on top Shockley Reed Hall recombination or trap-assisted recombination, we further reduce concentration of charge carriers, because we generate the same, keep in mind that for all these cases, we generate the same amount of free charge carriers. We generate the same amount of excitons, and then we reduce one because of geminate recombination. They are not splitted and don't contribute to free charge carriers. But then we have the same amount of free charge carriers as here for this blue line, but with additional mechanism of recombination, we lose more. So we don't generate more, but we lose more. That's why we lose in current, we lose in VOC, and also we lose in fill factor. So it's another feature of trap-assisted recombination. It also reduces fill factor. So we reduce technically all three parameters here in nominator, and definitely our performance, like PCE, drops. So that's why we need to understand physical nature of this geminate recombination and trap-assisted recombination, find the way how we quantify it in order to apply it to different types of organic solar cells, and understand how we can reduce it, or what is the relationship between these processes, undesirable recombination processes, with chemicals, for instance, a chemical structure of molecules which we use. So in terms
Can I ask a quick question, please?
yes, sure.
Just to understand the graph, the previous graph, the black line is basically the case when we don't have these recombinations. So it's more
Yeah, that's true.
optimal case, right?
Yeah, that would be ideal case which we would like to reach, but unfortunately we always have this recombination mechanism, and it's a matter how we first of all understand these processes, and second how good we are in terms of eliminating them from our devices in order to reach this kind of ideal case of described by the black curve. Okay, let's go further. So there are different approaches for studying different processes. And first of all, we start with generation. So it's the first process which happens in the active layer under shining light on it. So in order to quantify it, we utilize develop software for modeling optical field distribution within all layers of our device. So these dotted lines, they define different layers in organic solar cell. And what is the most important is here, which is active layer of the solar cell. So we need to know how optical field, the strength of electric field of electromagnetic wave, is distributed within the active layer for different wavelengths. So we do it for all wavelengths from the solar spectrum, which is like from about 250 to until the wavelengths which is defined by the band gap of semiconductor, where it still absorbs. So by applying this technique, so we need to know optical constants of all layers involved in the device structure. Definitely also optical constants of this active layer, mixture of donor and acceptor organic semiconductors. And by doing that, we can calculate the absorption spectra in active layer, some parasitic absorption in contacts at electrodes. So we don't want to lose light at electrodes because we don't generate excitons. We generate excitons only in active layer. So we want to design this device structure in that way that we have maximum generation rate within the active layer. And eventually, so what we can get, like some three-dimensional distribution, like some plot of generation rate as a function of wavelengths and position in our active layer. So we can really, within this nanometer range, see where most of charge carriers are generated. And it's not charge carriers yet, most of excitons are generated. And then we need to go to next step, which is Geminate recombination. We need to understand how efficiently these photo-generated excitons are split at the interface between donor and acceptor and form free charge carriers. For this purpose, one of the approaches is to use so-called time-delayed collection field technique. So the idea is that we have we apply some pre-bias, which changes, so we can test it at different biases applied to solar cell. And then we have very short pulse laser pulse. This very short laser pulse will generate some excitons in the active layer. And then we have some delay, keep this device at this pre-bias. And after this delay time, which can also be varied, we shift the pre-bias to large negative extraction bias when we create very strong internal electric field in the device and collect all free charge carriers. So we can, since we know the number of photons in this pulse of laser by comparing the total number of photons to total number of extracted charge carriers. We can determine the Geminate recombination prefactor, some coefficient which shows which fraction of excitons is splitted to free charge carriers. So if we have bad combination of donor and acceptor materials, this can be like maybe 10% or 20%. So only 20% of all photogenerated excitons will be split in free charge carriers. And that means 80% of potential free charge carriers, they are lost just because we couldn't split photogenerated excitons. That is very bad. That's why the highest performance devices nowadays, the best blends of donor and acceptor, they possess this prefactor, Geminate prefactor, about 95% and higher. Some reach even unity, like 100%. Then next step is to address non-Geminate recombination, because once we already described generation of excitons and Geminate recombination, so we already know how many free charge carriers are created in our active layer. However, in order to proceed further, we need to understand how many of these free charge carriers we will lose in the active layer of our solar cell while we try to extract them and collect at external electrodes. So one of the very simple technique to address this question, at least qualitatively, is to measure VOC, open circuit voltage, as a function of light intensity. So it has been shown by a number of research that this slope of open circuit voltage in semi-logarithmical scale against generation rate or light intensity, because they are linearly proportional. The higher light intensity, the higher generation rate of excitons. It changes, the slope can change from unity in terms of kT divided by Q, like Boltzmann constant multiply absolute temperature divided by charge of electron, to 2.0 kT. So this works for different, in two cases. When, first of all, when we have 1 kT over Q, bimolecular recombination mechanism dominates, and when we have 2 kT divided by Q, then we can claim that trap-assisted recombination mechanism dominates. Since bimolecular recombination is a fundamental feature of material, if we can create charge carriers by absorbing a photon in a material, that means that these charge carriers can recombine and emit this photon back. So in terms of detailed balance, bimolecular recombination is a fundamental feature of the material, and we cannot exclude it because it defines a theoretical minimum, like maximum of solar cell performance. However, if we see something what is larger than unity in terms of kT, we already see, okay, yeah, there is some issue with trap-assisted recombination, in particular in the bulk of the active layer. So this is very simple approach how we can distinguish what is the dominant non-Geminate recombination in solar cells. However, it's not enough, because recently when we got access to this new type of acceptors, non-Fullerene acceptors, I mentioned about them earlier, they help us to increase significantly performance of organic solar cells. We noticed that this slope, like open circuit voltage versus light intensity, is actually smaller than unity. So that is described by presence of surface recombination. So there are two types of trap-assisted. So as I mentioned before, there are two types of non-Geminate recombination, bimolecular and trap-assisted. And trap-assisted recombination in these devices, organic solar cells and also in perovskite solar cells, they share the same device structure configuration. Trap-assisted recombination should be also distinguished, and there should be trap-assisted recombination in the bulk of the active layer and trap-assisted recombination at the interface between active layer and electrode. So they have different influences on performance of solar cells. Both of them have negative influence, but they are different in terms of changing in parameters. So here we have an equation which describes total recombination current. It's like total recombination loss in organic solar cell, which includes all mechanisms of non-geminate recombination. So this is after this step of geminate recombination. By the way, worth to mention that geminate and non-geminate recombination, they are different not only in mechanism, but they are different in time scales. So recombination of charge carriers originated from the same exciton at the interface of donor and acceptor, it happens very quickly. It happens within up to 1 nanosecond. So if they survive these excitons and the splitted electron and holes at the interface, this nanosecond scale, then they already cannot recombine geminately because non-geminate recombination has time scale of microseconds. So we have different recombination mechanisms in different time scale. So all these 3 types of non-geminate recombination, which is bimolecular recombination, trap-assisted recombination in the bulk of active layer, and trap-assisted recombination at the interface, all of them are happening within the same time frame defined by from parts of micro to few microseconds. So previously, there was derived and developed quantitative models, analytical models for bimolecular recombination losses in organic solar cells and for trap-assisted recombination in the bulk. So my particular contribution to this was to propose a model which describes trap-assisted recombination at the surface of interface between active layer and electrode, and then we have complete picture of all different components of non-geminate recombination which cause total recombination current. Since we have such a model, we need to proceed further in terms of analysis of these processes. And here you have this N, which is concentration of free charge carriers. It is in all equations. So that's the first step to determine this concentration, some average concentration of free charge carriers in the active layer. For this purpose, we use impedance spectroscopy, and I will talk a bit more in details about it. We have eventually can describe different components of recombination processes in terms of recombination current and analyze them separately. For instance, here you see this blue dotted line. It's recombination caused by surface recombination at the interface between active and layer and electrode. And this is interesting because it contributes only very close to open circuit voltage. You see, only at large voltages. However, its contribution at smaller voltages or at negative bias is negligibly small. So we can neglect it. And this sharply and targetedly if reduces only VOC. However, short circuit current, which is measured at 0 volt, is affected by other mechanisms. So by introducing such a general analytical model, we can analyze each recombination mechanism in devices, quantify them, compare this between different device structures or different chemical structures of molecules which we use, and find some correlations. That is a very useful approach to proceed further in terms of increasing performance of organic solar cells. So I mentioned about impedance spectroscopy, and that would be useful to discuss it a bit. So so recently we just published a paper earlier this month on charge carrier density extraction from capacitance spectroscopy in organic solar cells, which summarizes different approaches to do this. But in order to introduce impedance spectroscopy, it's kind of useful to start with PN junction. So I believe that most of you heard about this, even it presented in high school physics. It's a contact of N and P type semiconductors, and depends on the level of doping. We can have symmetric PN junction or asymmetric. So here you can see asymmetric PN junction means that concentration of dopings in the P-type semiconductor is way higher than in N-type, and that's why the depletion region is totally formed in the N-type semiconductor. So this is the equation which defines the width of this depletion region. And if we apply external bias, if it's forward bias, we reduce the thickness of this depletion region. If it's reverse bias, we increase this width of the active layer of the depletion region. So depletion region means the region of the semiconductor which is depleted by charge carriers. So with internal electric field, all charge carriers are extracted from this region, and its resistance is very high. So it defines rectifying properties of PN junction. So if we look at this and see that it's somehow very high resistive layer between two conductive layers, so definitely it looks like a parallel plate capacitor. But in case of a PN junction, this capacitor has tunable capacitance. So it depends on voltage, applied voltage. It either larger for short, for narrower depletion region, or smaller for wider depletion region. So since this capacitance voltage dependence of a PN junction is a very important parameter, and we can use it in the Mott-Schottky relationship to plot 1 over depletion capacitance in square versus applied voltage from the intersection of this linear dependence with voltage axis. We define built-in voltage, the height of the potential barrier, and from the slope of this dependence, we can determine the concentration of doping. So it's important parameter to characterize semiconductors, which we use in our research or in making some devices. So in order to use this Mott-Schottky relation, we need to operate with the depletion capacitance of the depletion layer. However, when we measure capacitance, our impedance analyzer or capacitance analyzer considers every device in terms of this simple equivalent circuit where we have capacitor and resistor in parallel. However, it's not true equivalent circuit because we have also some series resistance. Even in this simple example, we have this additional series resistance, and it really messes things up because in terms of this simple equivalent circuit, we can get capacitance from measuring admittance, its complex conductivity, where we have conductivity, active component, and susceptibility, B, which is reactive component of complex conductivity. And by dividing susceptibility by angular frequency, we can get the capacitance, like so-called measured capacitance, that the capacitance which we get in our capacitance meter. And impedance spectroscopy, impedance actually is 1 over complex conductivity, it's complex resistivity. So it has also real and imaginary components, which for this particular equivalent circuit are defined by this equation. So this is some simulated spectral dependence of imaginary component and real component of impedance spectroscopy for this particular equivalent circuit. So what is the benefit of using impedance spectroscopy? If we measure, just operate with capacitance measured directly by our capacitance meter, it gives us depletion layer capacitance multiply this complex factor, which depends on resistance of the depletion region, frequency, series resistance, and if we compare, like see how the ratio between the measured capacitance and the depletion layer capacitance as a function of frequency, we see that at large frequencies for large series resistance, we have a huge deviation. It's like almost 2 orders of magnitude difference between measured capacitance and real capacitance of the depletion layer. That's why if we use this measured capacitance in the mentioned Mott-Schottky relationship, we will get just wrong concentration of doping molecules, and that will be misinterpretation of experimental data. However, with impedance spectroscopy, we can easily subtract the series resistance from the real component of impedance. So we measure this real component, we subtract series resistance, and then when we substitute these expressions for Z prime and Z double prime, we can get directly depletion layer capacitance. So we will get exactly that characteristic which is necessary to do correct analysis. So this is one feature of impedance spectroscopy, and of course we can apply it also to this correction, we do this correction in our research for series resistance, for parasitic inductance, and then corrected parameters we use to calculate concentration of free charge carriers, which is very important integral parameter in organic photovoltaic devices and in any devices, because concentration of charge carriers will define the net rate of recombination losses. Okay, so now let us switch to organic near-infrared photodiodes. So organic, in general, photodiodes, and in particular organic photodiodes, they can be used in very different applications. It could be some industrial application, some medical characterization, some imaging or CCD cameras, and also spectrometers, and this can be a wider range of possible applications. So there are important features of organic semiconductors, that they can be made flexible or stretchable, so it means that they can be conformable on different surfaces, so they can repeat surfaces structure, and they can be biocompatible with living organisms, so don't have some toxic elements which can be harmful for living organisms. And because of this flexibility in synthesis of organic semiconductors, we can get organic semiconductors with different properties, in particular band gap or like absorption profile. So we can shift it towards longer or shorter wavelengths, and that is really important because then we can change the wavelength region of photosensitivity, where these photodiodes can be applied within which spectral range. So there are 3 types of photodetectors. The first one is just a piece, like broadly described, piece of semiconductor material, photosensitive. in between two contacts. It can be bulk semiconductor or it can be thin film. Then we apply some voltage between these two contacts, shine light, and collect charge carriers. So this is the most simple photodetector. Then it could be photodiode. Photodiode, it has, if you compare this one, it very similar to solar cell device structure. So it's vertical configuration where we have some transparent substrate glass, then transparent cathode, active layer, and then anode. So they work actually every solar cell because this is structure of solar cell, however with some modification in terms of improving, modifying just interlayers. But in general, this is structure of solar cell. Every solar cell can work as a solar cell in so-called photovoltaic regime when it generates electricity under illumination, or in photodiode regime when we apply some reverse voltage and collect all photogenerated charge carriers which form photocurrent, and then photocurrent is considered as a useful signal, and we want to get this ratio of useful signal to the electrical noise when we have some signals, random signals in the dark, as big as possible. Then we will easily detect this photocurrent signal even when intensity of our light is very low. So we can detect very low intensity signals, convert like optical signals, and convert them in electricity. And there is the third type of photodetectors, it's phototransistor. So it is similar to the first case when we have a thin film of semiconductor between two electrodes. But in addition, we have some gate, so-called gate electrode, which is isolated from the active layer with a dielectric layer. And that helps us to modify with external gate voltage properties of the semiconductor and improve its performance. However, the biggest disadvantage of the first and third type of photodetectors is the time constant, so the time response. Since we have charge transfer along the plane of the active layer, it takes quite long for them to travel from one electrode to another. However, for photodiodes, we have vertical structure, and the distance between cathode and anode is very small. It can go up to 50 nanometers. That's why charge carriers can travel perpendicular to very thin active layer and be collected very fast. So that's why photodiodes, they always applied in cases where you need fast response and follow these very fast changing optical signals. So one of the examples of these organic photodiodes I was working on, it's a mixture also of some donor and acceptor, non-Fullerene acceptor material with the very narrow band gap. That's why we can absorb at long wavelengths up to 100 and 1100 nanometers. So this is so-called near infrared region. And that is very interesting application of organic semiconductors because so far until recently, we were working only with Fullerene based acceptors, and those possessed larger band gaps. So we couldn't reach high absorption in the long wavelength region, and organic photodiodes, near IR photodiodes just couldn't exist because we didn't have appropriate material for this application. But nowadays it's going further, and these ultra narrow band gap organic semiconductors allowed us to reach this high performance, high light absorption in the long wavelength region. So we made two types of devices, one with thin layer, active layer, one with thick active layer. And we see that this is some noise current as a function of frequency. It actually related to specific detectivity, which shows what is the ratio between useful signal to some electrical noise. And we see that with increasing thickness of our active layer, we can significantly increase the specific detectivity of our organic photodiode, which becomes comparable to specific detectivity of silicon photodiode. And it's kind of a big achievement for 300 nanometer thick piece of plastic. In comparison to 300 microns, it's like 0.3 millimeters of single crystalline silicon. So that is quite a nice result, and specifically it works at long wavelengths, which is very interesting for medical applications. So we have shown the time response of these devices. So in particular for the thick active layer device, you can see that at 200 kilohertz, so it's like the frequency of our light signal we shine on the photodiode, this electrical photocurrent response barely can follow it, because we don't see this square shape of the light we shine on it. However, already at 200 kilohertz, one order of magnitude smaller, we can see very nice response of this photodiode, which shows that up to these frequencies it can operate and adequately respond to light signals with this frequency. And then some application of this, as I mentioned, interesting for application in medicine, for monitoring like heart rate and concentration of oxygen in human blood. So because of heart rate, some period, we have extension and construction of vessels. So we have more and less blood to absorb this near IR illumination. Specifically, we were testing at wavelengths of 960 nanometers. So we don't see this light, and it can penetrate easily through human tissue, but it absorbed by our blood. And we can see here the response of electrical signal for heart rate. So we get heart rate period with extension and construction of vessels. And so in this experiment, our PhD student was doing some exercise, and after exercise, you see that the heart rate was increased. So it's kind of very basic application of this organic photodiodes, which can be flexible, conformable, so have a potential to be implemented in human tissue for constant monitoring. So before the end of my presentation, I would like to highlight that during last maybe 2-3 years, I had a chance to work on very broad spectrum of electronic and optoelectronic devices, and which cover almost all spectrum of electromagnetic waves, starting from X-ray and gamma ray detectors, some ultraviolet UV detectors, solar cells, which go up to infrared region, some thermoelectric generators, and also some electronic or ionic organic electronic ratchets, which convert some microwaves and radio waves in DC current. So of course, this wide range of devices will not be possible to work on them without collaborating with many people. That's why I would like to express my acknowledgement to my former host professors at University of California, Santa Barbara and Helmholtz-Zentrum Berlin, and my collaborators from all over the world, also funding agencies who supported my research.